Hello and welcome to the DevOps Essentials course. In this lesson, we will answer the question, what is DevOps? The term DevOps is short for development plus operations, and a lot of people define DevOps in different ways. So let's start with the Wikipedia definition. Now, DevOps is software engineering culture and practice that aims at unifying software development and software operations. Now, the DevOps aims at shorter development cycles. That also means that you're increasing the deployment frequency and more dependable releases in close alignment with business objectives. Now, that being the Wikipedia definition, and that's a whole mouthful of words as well, the whole objective is to understand this definition in this lesson. Now, there are certain myths that we must uncover, right? DevOps is not a tool. If somebody is telling you that, hey, DevOps is a tool or a set of tools, then they are not fully right. They are partially correct. But remember that DevOps is first and foremost a cultural movement. It is a culture of collaboration between developers and the operations people. This is a culture that has given rise to a particular set of practices, isn't it? When two different departments need to work together, they need to have certain practices, certain rules, certain guidelines. So DevOps is a culture, DevOps is a movement, DevOps is a set of practices. And it also means that it started from bottom up. So there's nobody in the management that woke up one fine day and said that, hey, development team and operations team, we're going to work together as one single entity. No, that did not happen. Now, because it is a bottom up movement, it means that it is started by people who practice it, right? It is by the practitioners for the practitioners. So the people creating the DevOps movement and the people participating in the DevOps movement are primarily those that are on ground doing the actual technical work of software development and system operations, right? It means that the DevOps practices does not come top down. It is implemented by the people who practice it, which is people like you and me who are doing the software development and also running the system operations, ensuring that your systems are patched, are secure, etc. So let's talk for just a moment what DevOps is not. Many people confuse DevOps with a set of tools that are associated with DevOps. I think I just mentioned this statement earlier as well, that DevOps is not a set of tools. So it is not Jenkins, it is not Ansible, it is not things like Kubernetes or containers. Well, while these type of tools are very important for us to succeed in the DevOps environment, but DevOps is not a set of tools. It is a cultural movement, like I said earlier, and these tools have been created as a result of that cultural movement. DevOps is also not a standard. There are no standards in DevOps. So if you're working in one company and you're talking to another colleague from your previous company, there may be a totally different set of standards and practices in that company. So there are certain best practices that many different people and organizations tend to follow. But there are no official standards that are set by the DevOps movement. DevOps is not a product. While there are several companies and individuals that have released products that support DevOps, DevOps itself is not a product. Again, it's a cultural movement. And finally, DevOps is not a job title. So DevOps is a culture of what? Of collaboration between developers and system operations people. It's about collaboration between different people across an entire organization. So it's not one person. It's not a single team and it's not done by a single group. Okay. So that being said, now you have a fair understanding about what DevOps is. Let's talk about what this course will cover. Now, we will go and talk about various things slowly. Let that information sink in. So we'll start with DevOps culture. We'll discuss in more detail the culture of collaboration between development and operations. Then we'll talk about some DevOps practices and things like continuous integration, server orchestration, monitoring, and some of the other practices that have grown out of the DevOps cultural movement. Then we'll talk about major tools that are associated with DevOps, such as Jenkins, Ansible, Docker, and others. And finally, we'll talk about the close relationship between DevOps and the cloud. Now that you know what DevOps is, you're ready to proceed with the DevOps Essentials course. Let's get started without any further delay. Thank you. We know that in the traditional model, the development and operations are considered two separate entities and they got different and opposing goals. The goal of the development team is to deliver features into the hands of the customers as quickly as possible. So the goal is speed, but the goal of the operations team is to maintain the stability of the system and also to minimize the downtime. The goals of the development team and the goals of the operations team become an opposition to one another in a traditional model. So when we think about traditional models, it's always these two teams working independently. But in a DevOps culture, it's always about collaboration between various teams that are involved in the project. It could be development and operations and all the teams as well. But we are mainly focusing on the development team and the ops team. The goals of these two teams are acting as an opposition to one another, right? Because one is concerned about stability and other is concerned about speed. Every time a developer tries to bring in a change in the system because of a new feature, he or she is trying to introduce an instability which the operations team does not like because they are trying to maintain stability. And the development team is trying to deploy as many changes as possible. Now, for the development team to deliver features into the customer's hands, they have to deploy changes, and those changes introduce a risk of instability. So these two goals are in opposition to one another. And even if the two teams want to collaborate several times, they wind up being in opposition because of these different and opposite goals. In fact, both the teams have certain KPIs, the key performance indicators. For the development team, the speed of delivery is a KPI, whereas operations teams are measured according to their minimized downtime hours. So they have a great incentive to fight against each other, to be in opposition to one another. Now, both speed and stability are very important goals, but the development and ops team are in opposition to one another, so neither of the teams are able to accomplish their goals properly. But let's take a look at how the DevOps culture fits in here and what are the goals of the DevOps culture. Now, in the DevOps culture, the dev and ops team are one group. They both share the same goal and they are both measured according to these same goals. Both speed and stability are very important. What DevOps culture has discovered is that when development and operations teams come together, they share the same goal, they prioritize speed, and they prioritize stability equally. So all the members of the team get together to find solutions, build tools, build processes that can allow an organization to have both speed and stability at the same time. So the development team gotta deploy frequently, gotta deploy quickly, and gotta make changes to the system in such a way that those changes are standardized in order to maintain the stability of the systems for the customers. And therefore, both of these goals wind up being met in such a robust environment that they stop fighting against each other. So, in a DevOps culture, the development and operations team are playing the same team, right? So, we are not playing like a sports football team where we are trying to see the other team lose. So, if one team lose, we're eventually hurting the organization. So, in a traditional culture, dev and ops team are opposing teams. So, for one team to win, the other has to lose. So, if you need to have very good speed of delivery, the stability has to be compromised and vice versa. So if you got to have good stability, the speed of delivery has to be compromised. But that doesn't happen anymore in the DevOps culture. Why? because the development and operations are playing on the same team. What's important about this is the fact that they have shared key performance indicators. They got shared goals and shared measurements. That means developers are accountable for stability now, and the operations engineers are accountable for speed of delivery. So you see the beauty of DevOps culture here, that the goals of developers are shared with the ops guys, and the goals of ops guys are shared with the developers. So eventually it all boils down to two things: stability and speed of delivery. Another parameter that lies between speed of delivery and stability is time to market. This is one of the goals that is shared by development and operations in a DevOps culture. What is time to market? Time to market is the time that it takes to take some work that the development team has created and then get it in front of the customers. So the amount of time you take right from the beginning, right from the time you start to write the code, and then all the way to finishing to deploy to the production and then to the working state is time to market. The faster the time to market is, the more successful the organization will be. Another goal is minimizing production failures, and this goes back to stability. The more production failures we have, the more instability you will have. So that's why we want the production to be stable. We want to have very less production failures. So the DevOps guys need to find solutions that will help us deploy solutions quickly, assist us in faster time to market, and minimize the number of failures. Another goal that goes back to stability is immediate recovery from failures. In real world, failures are going to happen. Mistakes are going to be made and things are going to break. So what do we do in such environments? The best thing you can do is to ensure that when those problems do happen, you can recover from them quickly and immediately. The faster you can recover from problems, the less impact they will have. The best case scenario is to recover from a failure even before customers notice it. And who makes it possible? The DevOps culture, the engineers, the developers who all work on the tools and design the processes make it possible. So DevOps is about development and operations team working together in a DevOps culture so that the developers care about stability as well and the ops guys care about speed. In the DevOps culture, the traditional roles of developers and the ops engineers will become obsolete because here the developers will start to take more and more responsibilities of the ops engineers. And don't get scared, ops engineers, because the ops engineers will take more and more responsibilities of the development folks as well. Now, there's no hard and fast rule, but when the two groups work together, it all looks a little bit blended. In the traditional culture, the developers throw the code over the wall, and when it's done, they wait for operations to get it deployed, right? Here, instead of throwing it over the wall, well, there is no wall here in the DevOps culture, right? There is nothing like that because dev and ops work together on the tools and the processes that they created. And what will in turn happen? Well, the speed and stability will increase because the developers and ops team work together to create and support those tools. So with this, the entire operations become even more powerful, right? Now, with all this story, I hope that you understood a little bit more about the DevOps culture, how it looks like, how they work together, and how we are removing the roadblocks from the traditional culture and the traditional roles of dev and ops are becoming obsolete here. Okay, so what do we do next? Since we spoke about certain stories so far, let's go listen to another story that will help us understand the differences between the traditional way of working and the DevOps method of working. So there will be different teams which are finger pointing at each other, right? The operations team says, hey, it's not my problem. And the dev team says, hey, it's not my problem. So let's take a look at how we are solving the problem here by understanding the differences. Thank you, and I'll see you in the next lesson. Hey folks, let's walk back in time to understand a brief history of DevOps. Now, in order to understand DevOps, you need to know a little bit about the agile software development movement. DevOps grew out of agile software development. Now, what is agile software development? Agile software development is a way of doing software development, and it primarily focuses on small, frequent cycles. Now, why do we need to have small, frequent cycles? Now, this will help us deliver functionality to customers quickly and quickly respond to changing business goals as well. The traditional way of doing software development was called as waterfall. And waterfall focuses on long planning phases, which is done over a period of several months worth of software development work, and then a long testing phase as well. So there is a long period of development work going on, a long testing period going on, and that means that there is a longer release cycle. No customer will be happy with that, right? Everybody wants products to be delivered quickly, especially in today's environment where things are changing at a rapid pace. Agile focuses on doing work in small pieces, releasing very, very frequently, sometimes every 2 weeks, sometimes every week, sometimes multiple times a week, with a focus on getting small pieces of functionality in front of the customer as quickly as possible just to make customers happy. Agile software development is called agile because it is indeed agile. It is flexible to the customer's needs and demands. So it allows a software development team to change direction very, very frequently and respond to changing customers almost immediately. So DevOps and Agile often go hand in hand. It can be very difficult to do Agile without DevOps, and it can be difficult to do DevOps without Agile. So let's talk about certain events that led to the creation of what we refer to as DevOps cultural movement. So we'll go back in time, talk about historical numbers and names, and refer to who was doing what in the last decade. In 2007, agile software development was becoming more and more popular, but it was suffering from a lot of friction between developers and operations as the developers were trying to release code more and more frequently, while the operations people were trying to maintain the stability of their systems. In 2007, an engineer with the name Patrick DeBoy, who had experience in the industry, and he was doing both development and operations work. He was working on quality assurance testing on a particular project and became frustrated with all the problems caused by the divide between dev and ops team. And he was a tester, right? He was working for a QA team, so he constantly had to go back and forth between them. And he saw that there were many issues getting in the way of releasing software quickly while maintaining stability. So you get the point here, right? We need to release the software quickly, but you don't want to hand over bugs to the customer, so the product must be stable as well. It took about an year, but the next year, 2008, Patrick DeBoy met Andrew Schaffer at the Agile 2008 conference in Toronto, Canada, and they began to start conversation about this divide between development and operations. How do they close the gap between the dev and ops team so that they can reduce the firefighting? So they then began to look at other people who are interested in bridging that divide and began to start online discussion groups to talk about this particular problem. What happened next was on June 23rd, 2009, there was a famous talk given by John Allspaw and Paul Hammond at the Velocity conference called 10 plus deploys per day, DevOps cooperation at Flickr. They were doing extremely large number of deployments every day, and they had pioneered some ways to do that through cooperation between dev and ops team. Now Patrick DeBoy was watching this talk via live stream, and it started a huge discussion on Twitter. In the same year, after a few months, on October 30th, 2009, Patrick hosted an event called as DevOps Days in Belgium. This was a small conference for both developers and operational engineers, and it spawned a continued conversation on Twitter with the hashtag DevOps. From there, DevOps grew into an organic grassroots movement all over the world and has continued to gain popularity. This collaboration between developers and operations people has led to the creation of many different tools that support the practices valued by DevOps. Since 2009, the DevOps movement has not stopped growing. What began as a small movement just between few people is today mainstream way of running the DevOps tool chain. This DevOps movement has also initiated the development of several variety of tools and has created an entire industry. It has completely changed the face of IT industry forever. DevOps has become the de facto standard. The companies that are growing the most, the companies that are most successful today in the IT industry are companies that are doing and pioneering DevOps. With this, now you know that DevOps is not new. It was started way back as a movement, and you now have a little insight into the DevOps cultural movement. As we move on and progress in the next set of lessons, we will discuss more about the DevOps culture, what it looks like, what are the goals of DevOps, the need for automations, and also various tools used in the DevOps tool chain. Thank you. So, what are we going to learn here in this lesson? Let's learn about two different concepts. One is the DevOps concept, and the other one is the traditional culture concept. Now, this is something where we already have an overview of these two concepts earlier. But as we go down and drill down through these chapters, we'll understand this whole concept better. In an IT organization, both the dev team and the ops team are in the business of shipping something to the customer, shipping a code or shipping an application. So both the theories that we're going to talk about now, the DevOps theory and the traditional culture theory, will just tell us how that process works. So let's understand how it is going on in the traditional culture or the traditional silo model. Now, silos. What is a silo? Silos are nothing but separated teams, teams that have walls in between them. The dev team and the ops team always had walls in between them. But there is another team which did great job testing what the dev team always did. They are called as the QA team. So now we got three teams here, the dev team, QA team, and the operations team. And every team has a wall in between them, and they were working in silos. So let's see what happens to the code that the dev team is initially creating in the traditional silo structure. First, of course, the developers will create some code, and when they are done, it just bumps over the wall for the QA to test. At this point, the developers are considering themselves to be no longer responsible for it because it's no longer in their bin, in the sense that they have done with the work is gone, until the QA team bounces the code back to them with a sequence of events that they should fix. So probably the QA team found a problem with the code. There may be certain bugs, there may be series of bug fixes, and the code bounces back and forth between dev and QA team until the QA team finally says that, okay, the code is good, there are no problems. So now it's out to production. So now the QA team is finished with the code. So they throw it over the wall to the operations team now. So it is now considered the responsibility of the ops team. But there may be a problem. Something may be wrong. The code probably might have introduced some kind of a bug in the production, or there may be several reasons why the code cannot be deployed in production. Now what happens? The operations team throws the code back over the wall to the dev team. The problem now here is that every group has its own domain expertise, and that domain expertise cannot be seen over the wall. It acts like a black box. That means that the developers do not really have much visibility into the production system, and the ops has very little visibility into the code. In several situations, when there's a problem, it may also lead to firefighting or finger pointing, where the groups will claim that it's not their responsibility. The ops team will say, hey, the systems are working absolutely fine. It's your code that has the problem. But the dev team says, hey, it's not my problem because the code works absolutely fine on my machine. And they don't know why it's not working on the production because they have no visibility into the production system. And the ops team simply assumes that the developers must be the key source of the problem. So, what's going wrong in this traditional silo model? The first thing is that the dev and ops team are something like a black box to each other. That means they have no visibility into each other's domain expertise. And that's what leads to finger pointing as well. The operations is a black box, so the developers do not really trust them. And in turn, the ops team do not trust the developers as well. They both think that the problem is caused by the other team. The second problem is that the two teams have completely different priorities, so they turn against each other and make them enemies. When the ops and the dev team probably meet in a cafeteria for a coffee or something, they think that, hey, these are the guys who are responsible for breaking stability because they are shipping the code too often, and every time they ship the code, they introduce problems into the production. And when the dev team looks at the operations team, they think that, hey, these guys do not absorb my code. They do not put in the code in the production. They are the obstacles. So they do not look at the ops team as the same team they are in. They view ops team as the obstacles to get the job done. So even if the two teams want to work together, the dev team and the ops team really can't work together because their deliverables are different. Their managers are different, and their managers will be holding them accountable to delivering the features of the application, which means deploying and making changes in the production. Ops team, as you know, is measured by the uptime of the servers, and their managers are holding them accountable for stability of the production system. And the changes that are being shipped by the dev team has led to bad stability. And that's why the teams are fighting against each other. So, what are the consequences of all this? We know that the whole black box theory led to finger pointing between the teams, isn't it? So, the traditional silo model is leading to a lengthy process of deploying code to the production. The lengthy process means a slow time to market. That means the development team cannot get the code to the customers quickly and efficiently. All of this is because there are a lot of things that are manual in nature, things are not automated, and the builds and deployments are totally inconsistent. For example, if the deployments are performed manually, the way in which the deployment occurs may depend on which operations engineer happens to be on call when the deployment happens. So, different people are going to do things different ways. Or even the same person may not do it the same way today that they did yesterday. This inconsistency is a major source of problems in production. And because neither team has visibility into other team's domain, they are spending a lot of time finger pointing. And it takes longer than it needs to identify and fix problems. So we can see that ultimately the traditional silo model is bad for both speed of delivery and stability. Why is it happening? It is happening because developers have this lengthy process that they have to go through in order to try and maintain stability. And yet, when problems happen, it's more difficult than it needs to be to resolve those problems. But let's look at what happens to the code within a DevOps culture. This story starts out the same way as the story of traditional silos. It begins with the developers writing some code. So when the developer commits their code, this initiates a series of automated steps, automated builds, automated integration, automated testing, and eventually automated deployment. Now, because all these steps are automated, the QAs can get their hands on the code almost immediately after the developers write it. What does it mean? It means that they can be testing constantly while the developers are writing that code. So it means parallel processing. And parallel processing means more efficiency, isn't it? Now, once the code is ready to be deployed to production, an automated deployment is kicked off. And the code gets to production in a consistent and stable manner. Now, what's more important to understand about a DevOps culture is this series of automated steps and this series of tools that enables the process collaboration between all of these teams. They all have to be onboarded with that, and they all have to buy into the process and contribute to creating this process in order to work for it for them. And the best part here when it comes to automation is that it's much easier to deploy code in a stable fashion, and therefore deployments can occur much more frequently. You can also have it done potentially multiple times a day, meaning that we are getting features and bug fixes into the hands of the customers much more quickly. But what happens if the latest deployment broke something? What happens in a DevOps environment when the developers do deploy some bad code and something is broken in production? What happens then? Well, one of the most important aspects of all this automation that goes with DevOps is monitoring. And so, in this scenario, some automated monitoring detected the problem almost immediately and notified the team that there was an issue. So, in this scenario, some kind of automated monitoring detected the problem, let's say almost immediately, and also notified the team that there is some kind of an issue. Now, the team is then able to use the same monitoring system, which is automated, and they can roll back the deployments. They are able to deploy a previously working version of the code very quickly, so the problem is fixed immediately. Now, usually a rollback might be considered bad for a development team, but not for the DevOps environment. Remember, we are all working together. So we did a rollback, but an hour later, the development team is able to deploy a fixed version of the new code containing the new feature sets that they were trying to deploy when something broke. So we had an immediate recovery from the problem that was introduced, and very quickly we were able to roll out a fix. So we have speed of delivery and stability even when there's a problem. And in several cases, the problem can even be fixed before customers really know about it. So, what is going right in this story? The right thing is that the dev and the ops team are working together to build a robust automation process for changing code quickly and reliably. And they were able to do this because they came together to prioritize both speed of delivery and stability. Automation is, of course, leading to consistency here. Now, every stage of the process, you think about building, testing, or deployment, it's all happening at the same time. And because it was all automated, it could happen much more quickly and much more frequently. Plus, you also have robust monitoring in place. So you got swift automated deployment process, and this is ensuring that the problems could be fixed even before users notice them. The dev and the ops are all working together upfront to build a good, robust process. And even if a code change happens and that code causes a problem, the users actually experiences very little downtime and sometimes on good days no downtime. So what do you think we should do DevOps? Well, we should do DevOps because it creates happier teams. The technical employees, both the development and operations guys, tend to be happier when they do DevOps. The engineers and the developers were very stressed when they were working in a traditional silo structure. Because things are automated now, it also means that your infrastructure and the code is much more stable. They can spend more time innovating and put less time putting out fires and doing firefighting. And people like you and me who are technical engineers and technical people love to innovate. The developers do not have to fight with the ops team to get their work done in front of their customers. The operations people don't have to fight with the dev team to keep their system stable. And all of this leads to happy engineering teams. It also eventually leads to happy customers. Of course, the most important thing for success of an IT organization is happy customers. DevOps lets us give customers the features they want much more quickly than a traditional model. And that also means that we do not have to sacrifice stability to do that. I hope this entire story of the DevOps culture and how it is different from traditional silo model helped us understand how we create happy customers and how DevOps teams are much more happier than the traditional silo based team structure. Thanks for watching so far. I'll see you in the next lesson. Let's discuss about the concepts and practices that support the DevOps culture. And we need to first talk about build automation. So, what is build automation? Build automation is automating the process of preparing code for deployment to a live environment. So, depending on what programming languages are used or what frameworks are used to create the code, many times code needs things to be done before it's ready for development. Probably it may need to be compiled, it may need to be transformed, and you may have to run the unit tests again. And that means taking all the steps necessary to give it a proper output before you start automating it. And the only reason you do it is to make sure that the output is consistent and the entire chain runs in an automated way. This is usually done using a build script or a build tool. So, what tools are used to do build automation? Again, depending on the programming languages and the frameworks that are being used, the build automation tool may vary. But that one thing that build automation tools will have in common is automation itself. So, what does build automation look like? Usually, the build automation tool will look like something where you can run a command line tool that will build the code. For example, it could be your configuration files or scripts that are treated as part of the source code. So, what that means is if your code is committed to source control, so it would be committed alongside the source code. Once that is done, you may want to check out the source code or clone the source code and use the same build tool to execute the build on your local machine. Build automation is independent of your compiler, or let's say the IDE. Back in the olden days, a lot of people used to build their code directly in their IDE. They would launch their IDE first and then they would click on the compile button and then click on build. And that would generate certain artifacts that could then be probably handed off to a deployment. But good build automation happens independently of the IDE, unlike your traditional build methods. Even if it is possible to execute the build automation without the IDE, it should also be able to work the same way outside the IDE. And this is important because it enables us to do things, for example, execute builds on a continuous integration server. Another important thing about a good build automation is that it should be agnostic of the configuration of the machine that it is built on. So if the entire code is built on your machine, I should be able to build the code on my machine or on the server inside my data center or probably in the cloud. And if we use a continuous integration server, let's say, we can build the code there as well and get the same results in all three places. So the $1 million question here is why should you do build automation? Well, first, automation is fast, right? Build automation is fast. It is used to automate the tasks that otherwise will be mundane and have to be done manually, and then you'll be just wasting a lot of time. Build automation is saving time for you. Secondly, and most importantly, I believe, is that build automation is consistent because the build happens in the same way every time. So we're trying to eliminate problems here. We're trying to eliminate any kind of confusions here as we compare it to the older manual builds. And when we were using manual builds, every time we used to run a particular build, we had different kind of an issue every single time you ran it, right? So build automation is repeatable. That means I can take the same version from the source control and build it multiple times and get the same result every time. So what you get here is consistency. Any particular version of the source code can be transformed into deployable code in a consistent way. Build automation is also portable. What does that mean? Now, here, the builds can be done the same way on any machine. It could be done on any of your team members' laptop or desktop. And then you can build the code on probably a shared server, like a continuous integration server. So the build code is not dependent on specific individuals' devices or even specific individuals, right? And now the final point here is that build automation is more reliable because it's automated now, just because we have fewer problems as compared to manual builds. So what did we learn here? Build automation, right? Build automation is really developer centric. The operations engineers really do not have to worry about it, but build automation is really important for the developers. So if you're a developer who's not using build automation, I highly encourage that you go ahead and start looking around these areas. And if you are an operations engineer, try and understand how important build automation is for the development team you're working with, right? It's a DevOps team. So you need to know about various tools the developers are using to do that automation for us, to ensure the stability of the system, right? And as an ops engineer, you do not find your dev team using the build automation tools, then you know what to do. Well, you'll go ahead and persuade them to use it, right? All right, that's all for now, folks. I hope you understood the concept of build automation here and the importance of it as well. Thank you. I'll see you in the next lesson where we'll talk about continuous integration. Thank you. Continuous integration, or CI for short, has been widely misunderstood term. Let's go back in time and understand how developers used to work. So let's say we got two developers, Joe and Mary, and they are writing their own code. So their job is to write code for the customers, and they probably are in two different geographical regions. So they're writing their own code. Once they are done with it, they will merge it so that the features and functionalities can also merge. This is usually done using a program, and the whole merging part really happens fast. So when that happens, there is a possibility of code conflict or merge conflict. So there may be few lines from Joe and few lines from Mary that will conflict, and during merge, it may create problems. There's also a possibility of few lines getting deleted. But if you scale this entire scenario, look at the real world, it's not just two developers, right? There are several developers. There are thousands of lines written, the millions of applications, and they are working on it for weeks and weeks. So that means that this entire code problem will be magnified. There will be several code related problems that will surface. And in the end, it's going to be a big mess. So what do we do to avoid this merge problem or the code merge problem? Now, in this modern world where we are building modern applications, let's see how it is done today. Going back to the same use case, we've got two developers who are writing their own code. And let's say they are developing a new piece of code for the new feature that customer requested. Now, when it's time to merge the code, it is done using some kind of an automation tool. This automation tool is watching the code, is constantly looking at it, and it grabs it, builds it, and tests it, or probably runs the unit tests. What will happen if it fails? If it fails, then a notification is sent to the team, and it tells that, hey, these changes that are done by, let's say, Bob and Alice has caused it to break. So go fix it. That means there is a safety procedure. Also, we have this build, right? This particular build that is built using the automation tool. So the QA or the testing team can do specific tests on that build. And that also means that the QA team always have a testable build. So what are the benefits you think with this discussion CI has or continuous integration has? Continuous integration ensures everybody's changes can integrate. You can catch the bugs early on and reduce any merge conflicts. Let's continue to talk about the practices and concepts that are associated with the DevOps movement, specifically as it concerns to continuous integration. We know that continuous integration is referred to as CI, and it is a practice of frequently merging the code changes that are done by developers. We spoke in the previous lesson that traditionally developers used to work more or less separately in silos. Individuals or teams would work on separate portions of the code base, and they might work for weeks or months before they would try to merge these things all together into one single application. But continuous integration means merging constantly throughout the day. So rather than merging large changes all at once, we are bringing together a lot of small changes continuously. And this is usually done with the help of automated tests, such as unit tests, that are used to automatically detect any problems that are caused by these mergers. Without automation, these frequent merges would be a lot of work. So, with continuous integration, it's necessary that merging would be an automated process. So, what does continuous integration look like? Well, continuous integration is usually done with the help of continuous integration server. And let me tell some examples. The most popular ones are Jenkins, TeamCity, Circle CI, GitLab CI, and there are lots of such tools in the continuous integration world. So we are doing CI in that CI server, and every time a developer commits a change in the code, the server looks at the change and automatically executes a build, and we are calling that as automated build. And there are automated tests that are running on the code. So the tests and builds are run against every single version of the code multiple times a day. Another important component of continuous integration is that anytime there's a problem with the build, we spoke earlier that the developers are getting notified automatically to get immediate feedback if the merge has caused any kind of problem. And if anyone commits code that breaks the build, that means that the build fails and it's just due to the failure of the automated tests. In that case, that person or team would then be responsible for fixing the problems or probably rolling back the changes immediately so other developers can continue working on it. That way, constant merges don't cause the team to stop working even when they do cause a problem. So we spoke about certain benefits of continuous integration in the previous lesson, but one of the greatest benefits that you will find using a CI tool is that you are ready to detect a error or a bug early on. It could be compilation errors that is usually caused when multiple developers work together and merge that code. And if the code doesn't compile, or one developer has changed something that causes an automated test to fail, that developer gets notified and they will then go ahead and fix those things immediately. It's important to detect the bugs early on. So sooner the bugs can be detected, the faster and easier they could be fixed. The continuous integration process and the tools really eliminates the confusion of the code scrambling and integration before that big release of your application. Now you can imagine the world without continuous integration, right? The developers are usually scrambling all the code to bring it together and they need to make it right before the release or the deadline. So they will have sleepless nights to bring that code to production. So with continuous integration, you will have happy developers because the code is constantly merged. So there is no reason to have large integration effort in the end. The continuous integration also makes frequent releases possible, right? Because the code is always kept in a state that can be deployed to production without a whole lot of work to get ready. The QA has the build in their hands, so they can go ahead and test it during the development process and not once the code is ready, right? Not in the end. So continuous integration encourages good coding practices. You need to have frequent commits throughout the day, which is then encouraged by developers to create a simple modular code rather than creating a giant complex mess that just creates confusion, and even after several months of work the code will never get to production. Overall, continuous integration is a very beneficial practice that keeps the engineers, developers, and of course the customers happy. In the next two lessons, we'll talk about the two important concepts which are interchangeably used, although they are different but closely related: continuous deployment and continuous delivery. Let's start with continuous deployment. So every developer starts to build the code on their laptop or some kind of a device and finally gets it pushed to a source control management system like GitHub or Bitbucket, Git or Azure repositories, or some sort of source control mechanism. Now, once the code is built there and pushed into the code repository, it then has to be built into some kind of a software. So the code has to transform itself into a software, which is done with the help of a build mechanism or a build software. Now that you got the code, you got the software, you don't push it to prod directly, right? There's some kind of a testing that needs to be done. But before we start to talk about the QA and the stage environments where we do regressive testings, let's go back in history and talk about a story. Now, this particular term, CD or continuous deployment, was coined by Timothy Fitz. Now, he has this theory, and this is also practically demonstrated in an application called as IMVU. Well, the theory is that the code can move from code stage to production 50 times a day. That means that as soon as the code comes into that source control, then with no human touch, it goes to production. Well, how would you do that? Automation is the answer. So the company IMVU had about thousands of servers to run thousands of tests in a very short period of time. And of course, they will have a series of monitoring on the prod systems. So just in case something goes wrong or any problems occur, they are then notified to the developers to fix it. Now, this setup that we just referred to is really extreme setup. Most companies do not have this set of resources to set this up. Specifically, there will be approvals to move the code from stage to prod. So continuous deployment is a practice where every change that is passing through all the stages of your production pipeline is released to your customers. There is no human intervention, and only a fail test will prevent a new change to be deployed to production. Continuous deployment is an excellent way to accelerate the feedback loop with your customers and take pressure off the team so that they can then focus on better activities. Developers can focus on building software and they can see the work themselves that it is going live minutes after they have finished working on it. Just to summarize, continuous deployment is the practice of frequently deploying small code changes to production. So with continuous delivery, we are keeping the code in a state that is able to be deployed at all times. With continuous deployment, we are actually doing the deployments frequently. Certain companies do the continuous deployment to production multiple times a day, but there is no standard for how often you should deploy. In general, the more often you deploy, the better it is. With continuous deployment, deployments to production are a routine commonplace event, and it's not a big, scary event like what it used to happen earlier. Continuous delivery is also an important aspect. So far, we understood continuous deployment. Let's learn about continuous delivery in the next section. Before we start talking about the concept of continuous delivery, let's talk about the Agile Manifesto, specifically the first principle. What it states is that it's really important to satisfy our customer with valuable software by making valuable changes. Of course, you're going to make valuable changes, and there's no point making a change without a value add-on. So in the previous lesson, when we were talking about continuous deployment, we understood that the code needs to be turned to software, and that process is the build process. So we got the code, we got the software through the build process. You do not go and directly deploy to the production, isn't it? We don't do that. So we do a lot of things in the middle, like testing. So there will be multiple environments in the middle depending on the organization you have, like a test environment, like a QA or stage. And that is a path to production in a continuous delivery pipeline. So let's understand the whole process here. The code gets committed to, let's say, the GitHub. Then there's a trigger that tells that there's a new code here. So the build server automatically does the build. It then triggers a deployment to the QA. It then automatically triggers our tests. And if they pass, they automatically trigger the deployment to the stage, which will then trigger more tests automatically. So the whole process is continuous and it's fast. At this point, we need some kind of a human interference or a process that will approve the movement of software from the final stage, the staging environment, to the production. Now that is typically a CAB or a change authority board that will approve this, and it's kind of a decision making. Now this is the idea of a continuous delivery. The idea to move from code to production, code from the source control manager to build to the testing environment, then to production. So here, when we refer to continuous delivery, we just mean that we want to keep the code in a deployable state. This means regardless of whether or not the decision is actually made to deploy a particular version of the code is always in a state that is able to be deployed, right? That means that the decision of whether or not to deploy is purely a business decision, but we as developers have kept it ready. Do we want to deploy these particular features at that time? And when you go to the development team and say that we want to deploy the code, then we are never going to say that, hey, there's a bunch of work that's remaining in order to get that deployment done, right? So the continuous delivery is a process to keep that code always ready for deployment. So don't use the terms continuous delivery and continuous deployment interchangeably, although you can abbreviate as CD. Of course, if you use CD, then people don't know whether you're talking about continuous delivery or continuous deployment. Although they are two separate concepts, they are very closely related. So what does it look like when you do continuous delivery and continuous deployment? Well, each version of the code goes through a lot of automation. It will go through a series of stages such as an automated build, automated testing, perhaps automated packaging as well, and maybe some manual stages. And the result of this process is that a version of the code becomes an artifact or a package that is ready to be deployed in an automated way. And when the decision is made to deploy, the process of actually deploying that artifact is also automated. To summarize, continuous delivery and continuous deployment are great practices for achieving a faster time to market. They will let you get features in the hands of customers quickly rather than waiting for a lengthy and cumbersome deployment process once every couple of weeks or once every quarter. There will be fewer problems caused by the deployment process, and many times the most difficult process in IT are the ones that are rarely used because the IT team doesn't have an incentive to really fix the underlying problems with those processes. Here, when you do the deployments frequently, that process is frequently used, frequently exercised, and the problems with the processes are easily discovered and quickly fixed. The more changes you deploy, the higher the risk. But then you make sure that you deploy small number of changes at a time. So with a continuous delivery and a continuous deployment concept, you're not doing that big bang, massive project rollout. And as a developer, you don't have to lose any of your sleeping hours to fix that bug in production. I hope this knowledge that's delivered through this medium is helpful for you to understand continuous delivery and continuous deployment concepts. Thank you, and I'll see you in the next lesson. Let's continue our discussion about DevOps practices with another interesting subject called as infrastructure as a code. Now this is really required where DevOps is practiced or where developers focus on automation. Infrastructure as a code is also sometimes termed as IAC, and it means managing and provisioning infrastructure using code and automation. With infrastructure as a code, instead of doing things manually to manage and provision infrastructure, we use automation. We use code to create and change things like servers, instances, environments, containers, probably clusters of containers, or an entire array of the stack of infrastructure that you're using probably for your web application. Traditionally, when you used to build servers, you used to build it with a graphical user interface, probably log into the virtual machine, probably log into that vSphere console and click on that file, new, virtual machine, and then follow through the wizard. Today, time to market is a key, and it's very important to spin up the infrastructure quickly so that your customers can then see the output quickly. With infrastructure as a code, you can build from a simple design like a two-tier load balancer environment to a very complex architecture involving several entities. So if you're thinking about what does this infrastructure code look like, all of this really sounds magical. Well, with infrastructure as a code, you will just be working with a set of code or set of files or maybe configuration with the help of certain automation tools to actually perform those changes. You would then commit those files to, let's say, some kind of a source control, which would treat it like a code, and then use an automation tool to implement, act on those changes defined in that code. With infrastructure as a code, provisioning new resources as well as changing existing resources are things that are both done through automation. So why should you do infrastructure as a code? The answer is same for automation, right? So why would you choose automation? Only to avoid any human errors, isn't it? But that's not the only reason. You get consistency in the creation and management of your infrastructure resources. Automation has the benefit and do things the same way every time. Humans tend to do things a little bit differently each time. So you get a lot of consistency in terms of how things are done with your actual environments. At this point, I would like to add another point about reusability. When you use infrastructure as a code, you can take that code, make a little bit of changes on that file, and you can spin up multiple environments with the same set of configuration. Or if you need to make certain changes, probably sometime in future, you can use that code again. So you get scalability of code. Just for an example, let's say that you need to add a new instance to a load balance server. What you will do is just go to the code, make those changes, and you're ready to execute that. If you provision the existing instances using infrastructure as a code, you can take that code and use it to provision a new instance that is configured exactly the same way as the existing instances in a very short time. Probably may take minutes or seconds to scale up and down. I'll tell you another great benefit of using infrastructure as a code, yeah? It makes your infrastructure self-documenting. With infrastructure as a code, your infrastructure and any changes made to it are documented through the changes made to those code and configuration files that are used to provision the infrastructure and execute the changes. For example, the way that a particular server is configured can be viewed in the source control as compared to a traditional model. Understanding how the server is configured was a matter of, let's say, who logged into the server, what commands were executed, and there was a lot of problems in those traditional days. So infrastructure as service is simplifying the complexity. If you'd like to spin up complex infrastructure that includes several databases, maybe you need an authentication server, a file server, let's say an application servers, and then replicate those environments one after another, probably a test environment, a prod environment, a QA environment, then you know what to do. You will just write that as code and use that code to spin up that infrastructure quickly so that you have identical infrastructure for several business units and several environments. So with infrastructure as a code, you are making your life much easier because you can manage that complexity of provisioning and managing the infrastructure simply by the use of code. I hope you can now understand the benefit of using infrastructure as a code. In the next lesson, let's go ahead and understand about configuration management. The infrastructure in an IT environment is prone to changes. Changes are very normal in day-to-day life in an IT industry, and they always need to happen. We always need to make changes in our infrastructure to keep them updated, to meet changing business needs, and to make sure that your environment is ready for production usage. Configuration management is about doing those changes in a maintainable way. Configuration management is a way of minimizing configuration drift. Now, what is configuration drift? Now, configuration drift is the accumulation of all the small changes that are made to the system over a period of time, and then it may cause those systems to become different from one another. When you started with your IT infrastructure, you might have thought about the baseline of the infrastructure components. But over a period of time, there will be several administrators working on it. That means the build numbers will change, the minor versions, the major versions may change, and hence they may drift away from what we originally thought. So if you think about it, every time someone logs onto the system and makes a change, there's a chance that they have now made that system different from other systems that you manage, but rather it should have been standardized. So configuration management is all about maintaining and changing the state of various pieces of infrastructure in a consistent, maintainable, and a stable way. Configuration management is about doing all those things in an automated fashion. So while we just spoke about drift and understood that drift is all about rolling changes from the point where we started and the point where we are today, and configuration management will help us minimize that drift by rolling out changes and managing configurations across a complex infrastructure in an automated and centralized way. The topic that we learned about earlier was infrastructure as a code. So you know what infrastructure as a code is doing, right? It is about provisioning infrastructure rapidly, as configuration management is about controlling that configuration. So controlling that deployment in an efficient way, in an automated way. So it looks like there is a close relationship between configuration management and infrastructure as a code. Now, infrastructure as a code is a very beneficial, very helpful tool that goes hand in hand with configuration management. So at this point, you may be thinking, what does this configuration management look like? So let's talk about that. As an example, let's say we need to upgrade a software package for a whole lot of servers in your data center. Now, what will happen without a good configuration management? What we would do as an administrator is log on to each server and perform the upgrade manually. The problem is this process can lead to a lot of problems. Maybe we forget about one of the servers because we didn't have a good documentation on it, and therefore the software package on that server was not upgraded. Or perhaps while we are in the process of rolling out those upgrades to a variety of different servers, there's a temporary version mismatch which causes something to break while we are in the process of manually doing that. Now, on the other hand, let's take a look at the configuration management from the other side. What we do is define a new version of the software package that we want in a configuration file or a tool, and then we use that tool to automatically roll the change out across a variety of servers within our infrastructure. So configuration management is about managing your configuration of all your server estate within a code on a particular server. And that server would then be called as a configuration management tool. All of this really saves time, isn't it? Because it takes less time to roll out the configuration from that centralized configuration management server, and you also get to see insights on that server. So not only are they able to roll changes out to all the servers, they give you insight into what the current state of your infrastructure is. So you will get a better understanding of what has been rolled out to your servers and what their configuration is at the moment. So configuration management is very good for maintainability, and this is very important because a maintainable infrastructure is easier to change in a stable way. Change always introduces the risk of instability. And that's one of the topics that we started our discussion on DevOps with, right? Ops team really does not like changes because it creates instability. And that's the whole reason we need to have controlled change to make your infrastructure maintainable and hence to reduce the risk. Configuration management minimizes the configuration drift. It means that it's easier to now keep a standard configuration across a whole array of servers when you really do not have to manually log into the servers and make those changes. So you are using automation to roll out those changes, and the configuration management server or a configuration management tool will help us do that. So the configuration management is very important tool for DevOps. A good DevOps infrastructure, specifically in the cloud, can become very complex, and you're going to need configuration management tools and servers in order to maintain that complex infrastructure in a stable and maintainable way. We're going to talk about orchestration a little bit in the next lesson, so that's when you will be able to join all the dots that we spoke about: understanding configuration management, infrastructure as a code, continuous delivery, deployment, and continuous integration. Thanks for your time so far, and I'll see you in the next lesson. In this lesson, we're going to talk things about specific to DevOps monitoring. Monitoring is an age-old practice where we collect the data and put that in a presentable format so that you can understand the performance and stability of various services in your infrastructure. In the DevOps culture, monitoring is very important. It supports the frequent deployments and faster time to market by allowing you to quickly respond to any problems that are caused by those frequent deployments. And of course, it supports stability for the same reason by allowing you to quickly address any problems that could be affecting the stability. There are various monitoring tools out there in the market, and all such monitoring tools will be collecting data about things like memory usage, CPU, disk input output, and various other resources that you can configure over time. You can also collect application logs from your Windows Server, information about network traffic from your firewalls, and lots of other data that can be used to gain insight about the health and performance of your infrastructure. The collected data is then presented in various forms. So you can have the pictorial representation in the form of charts, graphs, so that people who look at it will know how things are performing. You can also use this data in the form of real-time monitoring, real-time notifications about problems. That means that if your monitoring tools notice that there's a problem in your production, they would immediately notify you so that you can do something to fix that problem even before customers notice it. So, what does monitoring look like? What one as a DevOps practitioner must be really curious about is a real-time notification. So let's say that the performance of our website starts to slow down. Response times are getting longer and longer. The monitoring tool of your choice is watching our response times and notices that they are growing and immediately notifies the administrator so that the admin is able to intervene before that performance degradation actually impacts your customers. Another use case of monitoring is troubleshooting or postmortem analysis or forensics. That means looking at something after something happens reactively. So let's say that something went wrong in the production last night. It's working now. The production is up and everything is alright. The customers are happy. But we still want to know the root cause of the problem and what caused the problem last night. Monitoring tools come to our rescue because it has collected a lot of data during the outage, and that data is now available to us. So in this scenario, let's say we looked at the data and the developers and operations engineers are able to determine the root cause of the last night's outage. It could be happening because of a poorly written SQL query, but now that you know the cause, you are able to fix it. The sooner we detect a problem, the sooner we can fix it. We want to know about a problem before our customer does. When something goes wrong in the production, the worst case scenario is to find out about it by getting a call from a customer. I want to know about the problem before the customer calls me, and potentially it will be great if we can resolve it before the customer starts to experience the problem. Monitoring offers better root cause analysis.
The more data we have about our production systems, the easier it is to determine the root cause of any particular problem. Without any good monitoring, we would wind up making guesses about what caused the problem to occur in the production. Therefore, we do not really have the tools or information that we need to effectively fix those problems for the future. Monitoring is very important within the DevOps context. Monitoring is one of the primary ways that we offer visibility into the production systems across various teams, not just the operations team, but also the development team. Good monitoring tools gives us the useful data that could be used by both developers and operations people to understand the performance of code in production and potentially do optimizations to improve the performance. And another great benefit of monitoring is the automated response. The data that comes from monitoring tools can be used alongside orchestration tools. Another type of automation tools to provide automated recovery from the failures can be done if you have integration done with orchestration. Monitoring tools can be used to detect problems. For example, monitoring tool is essential to bring together fast delivery and stability, specifically in complex environments when your environment is operating at a very large scale. Microservices is another hot and buzzword these days. In this lesson, let's go and understand what microservices are. Microservices is a concept of a software architecture. A microservices architecture will break an application into collection of small but loosely coupled services. In the traditional design and in the traditional architecture, all the features and services that are part of the application were part of one large executable, and we used to call them as monolithic designs or monolithic architectures. We used to keep them as one giant entity. Microservices are small pieces that are broken up into their own individually executable portion. So each microservice implements only a small part of an application, providing a certain functionality. And most importantly, microservices are loosely coupled. What does that mean? It means that the microservices interact with each other and with the application overall using a stable and well-defined APIs. And that means that they are dependent on one another. As long as these APIs are maintained, changes can be made to microservices without disrupting the rest of the application. So, just to picture what this actually looks like visually, a monolithic would contain all the different parts of an application. So, that application needs to handle authentication, maybe maintain customers' databases, payment processing, and all such functionalities will be part of one single executable. With microservices, what we are saying is that let's go ahead and split them up into multiple pieces. So if there is a front end user interface, which is its own separate entity and is communicating with, let's say, an authentication service, a customer information service, an inventory service, maybe a payment service. So these services are all separate. And they do not necessarily even need to live in the same place. They don't need to be built on the same technologies as well. They just need to communicate with each other over standardized APIs in a microservice architecture. So microservices is all about breaking up a large application into individual functional components. So what do microservices look like? Well, there are different ways to structure and organize a microservice architecture. Have you specifically decide to break up the functionality of an application into microservices could change depending on what type of application you're building and what makes sense at that time. Let's say you got a simple e-commerce application where you would like to design a shopping cart for people who would like to buy accessories for their pets. Your customers will go ahead and search for what they want, fill out the form out there, and potentially process payments to purchase things from that pet store. We might even have the pet accessory service that gives us information about all the accessories that are available for different kinds of pets. In the backend, you may have customer details that will maintain all the information about your customers. We might have an authentication service that is used when customer wants to log in. We might have an accessory service so the customer can fill out the form and then go ahead and purchase it after the payment processing is complete through your web app. Now, each of these services would be built within its own code base and would be separate running process because of course we could run any of these services on multiple nodes, and each of these pieces of the app can be coded, built, deployed and scaled separately from one another. So why would you want to use microservices? Well, one major advantage in this case for microservices is that they are very good in supporting modularity. So the microservices would help you and encourage you to build modular apps in a monolithic application. While the individual pieces become tightly coupled, and over time it can become very, very complex. So if you have been a developer for large and complex applications, you may have experienced this that over a period of time, in several years, eventually the application gets so large that it's difficult to maintain. And it's very difficult to change anything without breaking something. So you make a small change, and there's a whole lot of testing efforts that's required in order to ensure that that change did not break something. And this also means that it will slow down your ability to deliver new features and functionalities. Well, with microservices, each one of these pieces has its own separate, maintainable, and much more simple entity. Microservices also offer technological flexibility because each piece of the application is separate from another and they can communicate with each other over standardized APIs. Another point to remember is that each piece of the application does not necessarily need to be built using the same programming language and technology and other parts of the application. That means for any individual piece of the app, you can use the tool that is best and that is well known to do that specific job. It also means that you as a developer can adopt new technologies over the lifetime of the application. You can build new functionalities with the help of new languages, new technologies, and they will just work fine because they just need to work with standard APIs. Microservices offer optimized stability. That means that you can scale individual parts of the app based on the resource usage and load. With a monolithic application, if you want to scale the app, you want to dedicate more resources to it or build additional nodes to support it. You have to dedicate those resources to every single feature of the app because the app is one giant executable. So in this particular example here, you can scale the authentication module, the customer info module, scale the inventory and the payments module separately, which becomes very difficult and cumbersome in the monolithic architecture. Although all of these benefits are great, but one thing to keep in mind is that microservices is not always the best choice. If you have a smaller, simpler app, sometimes a monolithic can be easier to maintain and manage. But once you have a big, complex application and a lot of different parts and pieces and functions to it, microservices is the best option to choose. Just to summarize, microservices is an important concept in the DevOps world, specifically when it comes to managing large and complex applications. Each individual piece can be deployed and scaled separately, and microservices are great in supporting the fast speed of delivery coupled with stability. Let us discuss about the tools that are in the world of build automation and continuous integration. At this point, I would like to summarize what build automation and continuous integration is. Build automation is the automated process of building code in preparation for deployment. And the tools that you use for build automation generally depends on the programming languages and the frameworks that have been used to create that code. For example, build automation for Java is Ant, which is a very old tool, and the tools that are most used today are Maven and Gradle. JavaScript has tools like npm, grunt, and gulp. Make is a build automation tool that Linux users might be familiar with because it is widely used in the Unix based systems. Another interesting tool is Packer, And this is a build automation tool that is not geared necessarily towards building code, but building virtual machine images and even containers. It's a tool for building containers that works just like a build automation tool that you would use in order to build code, but it builds machine images and containers. Now, what is continuous integration? Just to summarize that as well, continuous integration is the practice of continuously merging the code into a single branch or the main line, and these tools usually consist of a server that does continuous integration and integrates with the source control. So every time your code is changed in the source control, the continuous integration server will respond by executing an automated build. So if we used one of these automated build tools, like the ones that we just mentioned, could be Maven, Gradle for Java, our continuous integration server is going to execute the Maven or Gradle build and perform the build in response to a change in the source control. One of the major continuous integration tools is Jenkins. Jenkins is an open source tool from Hudson. Now, since Hudson is controlled by Oracle, the open source developers on the project became concerned about the level of control that Oracle had over the Hudson project. So they forked the project and it's now called as Jenkins. Jenkins is very widely used. It's a Java servlet based system. So Jenkins itself is a Java servlet web application. It has a web interface where you can go configure your builds and it will see your changes in the source control and automatically execute builds based upon those changes. Another popular CI tool is Travis CI. Travis CI is an open source and it is built around GitHub integration, so it integrates very well with GitHub. If you use GitHub for source control, Travis CI may be a great option. I'll tell you one interesting feature of Travis CI. Now, the Travis CI executes each build in a clean virtual machine. And that can be very important because you do not want multiple builds running on the same continuous integration server to affect one another. As much as possible, you want your builds to be clean. You want them not to be affected by anything else. You want them to be consistent and they should be happening the same way every time. And executing each build in a clean virtual machine is a great way to ensure that it occurs. Another continuous integration tool is Bamboo. Now, Bamboo is not open source tool. It's not free. It's an enterprise product by Atlassian. However, if you use other Atlassian products like, let's say, Jira and Confluence, then Bamboo has a great out-of-the-box integration with those Atlassian products. All of the continuous integration tools that have been merged here are great tools, but they are not the only ones. There are several others. And I would continue to say this again and again, that the list of tools that we're specifying here are not the only ones. There are a lot of them, but I'm just listing the most popular ones. So see if you can find other tools that will help you succeed in doing continuous integration. Let's talk about configuration management in the next lesson. What is configuration management? Configuration management means managing and changing the state of pieces of infrastructure in a consistent and maintainable way, usually using automation. Continuous management tools are a great way to implement infrastructure as a code. This is one concept that we spoke about earlier in this course, and a good configuration management tool is not only going to act as a configuration management tool, but it's also gonna support infrastructure as a code. Now, we are going to talk about a few of the most popular configuration management tools, and one of the major configuration management tools is Ansible. Ansible is an open source tool and it's able to make use of something called declarative configuration. A declarative configuration means that rather than simply laying out a set of steps that are required like a script in order to configure an environment in a certain way, you describe the state that you want the environment to be in. The tool determines what is necessary in order to get the environment into that state, and Ansible uses declarative configuration. Now, some people will debate that, and some people might say that Ansible is a little bit more procedural because it has a concept of tasks where you do one thing after another. But the actual baseline design of an Ansible module, which is what Ansible uses to make changes to the system, is ultimately based on a declarative philosophy. And Ansible uses YAML, which stands for Yet Another Markup Language. Now it uses YAML configuration files in order to specify configurations. An important feature of Ansible is that it does not require a centralized server. Many configuration management tools use a centralized server that pushes out changes to individual hosts or environments. Ansible does not require a control server. You can push changes from your laptop or really from any machine. However, Ansible does have a product called as Ansible Tower, which is capable of acting like a control server. It's not required, but what that allows you to do is to take Ansible automation and make it available to others. You can put a lot of things inside the code, like permissions that you want to give around, and give certain individuals access to perform certain pieces of automation through that server. And the best part is that Ansible does not even require agents. Many configuration management tools require a piece of software, an agent, to be installed on each individual machine. But Ansible does not require any agents. It simply uses the existing technology of Python and SSH to connect to the host and make the changes that it needs to make. Another popular configuration management tool is Puppet. Like Ansible, Puppet also uses declarative language or a declarative configuration, meaning that you describe the state that you want the machine to be in, and Puppet figures out how to get to that machine into the state you want it. In Puppet, you primarily manage state through a user interface, which means that for some of it, it will become easier to use. And in Puppet, you can create custom modules using Puppet domain specific language. So if you want to create certain functionality beyond what Puppet includes out of the box, you are going to need to learn the actual Puppet code or Puppet DSL. Puppet does use a control server and it pushes changes out to the clients using that control server and agents installed on each one of those clients. So the Puppet uses a control server agent architecture. Another configuration management tool, in fact, it's very famous in the enterprise world, is Chef. Now remember that Ansible and Puppet are using declarative configuration, whereas Chef is more geared towards procedural configuration. That means that instead of declaring the state of that machine that you want that to be in, you basically write scripts or a set of steps that are required to get the machine into the state that you want. Just like Puppet, Chef uses an agent server model. So there's a centralized server and their agents are installed on each one of the clients. Chef configuration is written in a domain specific language that is specific to Chef. So just like Puppet, if you want to use Chef, you're probably going to have to learn their domain specific language. Let's talk about Salt. Salt is another configuration management tool. This is made by a company called as Salt Stack, but the actual tool itself is called as Salt. Salt uses declarative language or declarative configuration, so you can describe the end state of the clients and the machines that you want them to be in. Just like Chef and Puppet, it's an agent server architecture, but it refers to its agent as minions and the server as master. However, Salt has now released support for agentless architecture as well, so you would still have the master server, but you don't necessarily need to install any agents on every node or a minion. Just like Ansible, Salt uses YAML based files for configuration. An interesting feature of Salt is that it supports event driven automation. What this means is that Salt can actually respond to events in real time. So an agent can actually detect things happening in one of your client servers, and that event can then kick off automation. Other configuration management tools are dependent on humans or scheduled processes or external tools that integrate with the configuration management tool in order to kick off their automation. But Salt has built-in support for responding to real-time events as they occur. These are just few of the configuration management tools that are available, and we have barely scratched the surface of any of them. So I would highly recommend that if you are interested in doing configuration management, please go ahead and read further about every one of these tools and maybe take a look at the atomic periodic table that I shared earlier. For now, let's go ahead and take a look at the tools available in the world of virtualization and containerization. Virtualization is not a new term, although containerization has been there from a very long time, but it has become a buzzword very recently. Let's talk about the tools used in the world of virtualization and containerization. Virtualization means managing resources by creating a virtual layer on top of your physical machines. Traditionally, we used to deploy physical machines for every single application. But with virtualization, we have learned the art of creating virtual resources on top of the actual hardware resources. Now that gives us much more flexibility, isn't it? So virtualization's tools make use of hypervisors. What is a hypervisor now? A hypervisor is a program that runs on the bare physical metal and allows you to manage virtual machines running across a variety of physical hosts. There are certain examples. There are well-known virtualization tools available in the market. So that's VMware ESX, ESXi, Hyper-V from Microsoft, Zen Server from Citrix, and there's a long list. But these four tools that I just mentioned are one of the top in the Gartner chart. But the main reason I want to talk about virtualization was that we could go on and talk about containerization. Containerization is the next step beyond virtualization. Containers are lightweight. They are isolated packages. Now these contain everything that is needed to run a piece of software. They require very few resources as compared to a virtual machine. Virtual machine contains an entire operating system. Plus, it contains virtual versions of the hardware. But containers, as they are very lightweight, they contain only the bare minimum of what is needed to run the software that is installed on the container. The virtual machine has an entire operating system built into it. A container only simulates the operating system, and it does it in very thin, efficient, and lightweight fashion. Containers have most of the benefit of virtual machines while using much fewer resources and being much easier to manage. The primary containerization tool that we have in today's world is Docker. You might have heard of Docker several times, as that is the leading container technology. Containers are still relatively new, but they have been hanging around for as long as other technologies that are out there. But keep in mind that containers are extremely useful in the DevOps world. One of the DevOps practices that we talked about earlier in this course is the practice of orchestration. One of the easiest ways to do orchestration is by using containers. And we're going to talk about orchestration tools later on in this course, but please understand that orchestration and containerization go together very well. Now, the benefit of containers is their portability. Your developers can run a container that is exactly like a production container on their own laptop. Now, this increases the visibility into production and also offers consistency between development environments and production environments. So, if you're interested in exploring containerization, I highly recommend that you check out Docker, as that is the open source and you can learn the basics in a very short period of time. Let's talk about the monitoring aspects and the tools used in the monitoring world as far as the DevOps is concerned. Thanks for watching, and I'll see you in the next lesson. Monitoring is not a new concept, and we've been doing a lot of monitoring with various kinds of tools for monitoring the state and performance of our applications. The couple of different types of monitoring and some tools only cover one of those domains. One type is infrastructure monitoring. Infrastructure monitoring focuses on data related to the health of your infrastructure. Things like CPU usage, memory usage, networking statistics. Now, these are the things that the tools for monitoring will do for us. There's another type of monitoring which is APM or application performance monitoring. This focuses on the performance and stability of applications that are running on your infrastructure. And this will take a look at things like response time for web applications and also the application logs. Some tools cover both of these domains. There are other tools that will focus on something else probably, but let's first talk about tools that are good at infrastructure monitoring. The one that's in my favorite list is called as Sensu. Sensu is designed as a modern replacement for Nagios. In fact, they have built-in migration paths from Nagios to Sensu. So if you are currently using Nagios, Sensu is something that you might want to consider because it is much easier to migrate to it. Sensu uses a client server, a server agent architecture, just like Nagios. So there's a shared central server, and agents are then installed on every host that performs the checks on each one of those hosts. Sensu, however, is a little bit more modern and sophisticated than Nagios. It's more scalable, and the agents push data to the broker rather than just pushing them directly to the centralized server. Another tool that's very famous in the infrastructure monitoring world is New Relic. New Relic is actually a SaaS or software as a service solution. So their centralized server is located in the cloud. However, you must still install agents on each one of those services that you want to monitor. So your services are going to communicate through this agent to their cloud server to send it data. New Relic supports a wide variety of metrics, and even though it's a good infrastructure monitoring tool, it's also a good tool for application performance monitoring. So let's talk about application performance monitoring tools. One major tool is AppDynamics. AppDynamics collects data points about applications and presents them in a centralized dashboard. One of the benefits of AppDynamics is its code level diagnostics. Developers would love this. It's often able to identify the source of problem or performance issues down to the line of code that is causing the problem. AppDynamics also uses a server agent or client server agent architecture with a centralized server and agents installed on each service. And we should also talk about New Relic here because that is also a good infrastructure monitoring tool and also does APM, which is application performance monitoring. A lot of DevOps practitioners talk about aggregation and analytics. Let's talk about that for a minute since we're talking about monitoring anyways. Aggregation and analytics are about what we do with the data once we have collected it. Most monitoring tools come with some kind of an aggregation and analytics features. Aggregation and analytics are going to be the charts and the graphs and the notifications that come out of your monitoring tool. It's important to consider not only what type of data a tool is able to collect, but what features it has for allowing you to present and analyze that data. A great tool for aggregation and analytics is Elastic Stack. Elastic Stack allows you to pump data in, and through its aggregation engine called as Kibana, you can quickly aggregate and easily detect and diagnose problems. Now there's some overlap between these tools. Elastic Stack also comes with agents, which it refers to as beats, which are able to actually collect both infrastructure and application data to do both infrastructure monitoring and application performance monitoring and obtain the data, which Elastic Stack can be then used to perform aggregation and analytics. There are many different ways you can use the tools, but ultimately you may wind up using multiple monitoring tools in combination in order to achieve your monitoring goals. Monitoring is so important for the success of your DevOps design. At this point, I highly encourage you to go ahead and take advantage of some of these monitoring tools. Look around the options that you have in the world of monitoring specific to DevOps. Orchestration means automation that supports processes and workflows, particularly the provisioning of resources. So, orchestration lets us do things like scale up, scale down an application based on request. And that means assigning more resources to them or taking away resources when they are no longer needed. It also allows us to do things like auto-scale applications based on usage, so we can actually detect increase and decrease in the usage patterns and automatically scale up and down based on response. Orchestration also lets you do things like create self-healing systems, so we can detect unhealthy nodes in a load balanced pool, remove them from the pool, and automatically replace them with healthy nodes before users experience any problems. One of the great orchestration tools that's available here is the Docker Swarm. Docker Swarm is Docker's native orchestration tool, and it is created explicitly for the orchestration of Docker containers. Orchestration goes very well with Docker containers because the containers are lightweight and self-contained that could be spun up or spun down very quickly. Containers are very efficient to use alongside orchestration tools that control when and how they spin up and down. And containers tend to make orchestration easier. So if you want to do orchestration around your Docker containers, Docker Swarm is a great way to do so. Another very powerful orchestration tool is Kubernetes. It is called as a gold standard in the world of orchestration in DevOps. Kubernetes is open source and it uses an orchestration server to control the orchestration of your resources. Kubernetes is able to manage your containerized apps across multiple hosts so that you have a pool of resources that may consist virtual hosts, probably bare metal hosts, or even cloud resources. So Kubernetes is able to utilize that pool of resources to orchestrate your actual application containers and provision resources to them as necessary. Another important orchestration tool is Zookeeper. Zookeeper is an open source solution developed by Apache Foundation, and Zookeeper can work alongside Kubernetes. Zookeeper includes a centralized service registry, and much of its functionality is built around that concept. The services spin up and spin down, and they register themselves with a centralized service registry. And that is done in order to help the services locate one another through the service registry. So that means that the service registry will act as a center point for orchestration features. Another powerful orchestration tool is Terraform. Now, Terraform is a tool that's a brainchild of HashiCorp. Terraform combines orchestration with infrastructure as a code. Now, some people think of Terraform as more of infrastructure as a code tool or a configuration management tool, something a little more similar to Ansible. But Terraform is really built around the philosophy of orchestration. And that means that Terraform crosses both of these territories, but it's really focused on orchestration. Terraform works really well alongside other tools like Ansible, so you can use Terraform and Ansible together. It also works really well with AWS and it integrates with Kubernetes. So you can use Kubernetes to do high level orchestration and implement a little bit more of the detailed configuration within the Terraform scripts. So when you are looking at tools you want to use to do server orchestration, you do not necessarily need to choose between all of these tools. Many times you may want to use more than one because they can work all together with different tools handling different pieces of the big picture that is server orchestration. Now we know that server orchestration is a large and complex topic and there are different tools and there are several tools that can be used to do it. In this lesson you just had a brief introduction of some of the major ones, but you're definitely going to bump into more of these when you do some more research. So if you want to enter into the world of orchestration, I suggest that you go ahead and research about it and see how it actually works. The benefits of orchestration are incredible. and it's well worth doing research and learning what you need to find the tools that you need in order to do it well. DevOps and the cloud, although are not married to each other, but the practices of DevOps have been widely used in every cloud platform. So far in this course, we discussed about the practices and concepts and tools that are associated with DevOps. Now we're talking about how DevOps will contextually fit in the cloud arena. There's a very close relationship between DevOps and the cloud. It's important to understand that DevOps and the cloud, although are very closely related, but they're not the same thing. DevOps is a culture of collaboration between development and operations, and it can happen inside the cloud or outside the cloud. The cloud, in its simplistic terminology, means remote servers on the internet that offer services in place of locally hosted solutions on your premise in your data centers. You might have heard of people saying cloud is just someone else's computer. So DevOps is a culture of collaboration that can happen with cloud or without cloud. The cloud means utilizing remote services in place of locally hosted solutions. Although DevOps and the cloud are not the same thing, the culture, the practices of DevOps are very useful in the world of cloud. DevOps and the cloud work alongside with one another. You can also say that they kind of grew up together, and in many ways, cloud services are built upon DevOps practices. Cloud services can also be a great tool for DevOps. And there are several cloud services that offer features and functionalities that will support DevOps practices and will support you in using the DevOps tools. We'll be talking more about this relationship, but in order to understand this further, we need to talk about different architectural stacks that you can find in the cloud. But before that, is there a stack in the traditional world? In the traditional architecture, you would be managing your own data centers in your premise. So you would start with the networking layer, the networking infrastructure. You have a storage infrastructure, and potentially you may have virtualization. And on each of the servers, you have an operating system, the middleware, probably the runtimes, databases and applications, and the whole stacks that will require for an application to perform properly. In the traditional stack, you are responsible for managing and maintaining every layer of the infrastructure. So with the traditional stack, you provide all of the infrastructure that is necessary in order to run your applications. Now let's take a look at some cloud architectures. Well, the first type of cloud stack is infrastructure as a service that you know also prominently called as IaaS. Now with the infrastructure as a service stack, someone else provides the low level infrastructure. So the cloud provider typically provides you with a bare operating system, and then you are responsible for being able to log into those machines and do any additional configuration beyond just a bare operating system. Certain examples of infrastructure as service would be Amazon Web Services providing EC2 instances, Microsoft Azure virtual machines, and also containers. Google provides infrastructure as service in the form of a compute engine. So just to be clear, I'm not saying that Amazon, Microsoft, Google platforms are entirely infrastructure as a service. It's only these specific use cases like EC2 instances or virtual machines from Azure and containers and the Google Compute Engine, also called as GCE, are characterized as infrastructure as a service. Another type of cloud stack is platform as a service. Now, with infrastructure as a service, the cloud provider provides you with the bare operating system that you then have to configure. But with platform as a service, they provide you with a standardized OS, and then you deploy your data layer, your applications on top of that. You are only responsible for managing the application and the data. Some examples of platform as a service would be AWS Elastic Beanstalk, Heroku, and Google App Engine. Let's talk about another important aspect of the cloud architecture, which is software as a service. So with software as a service, everything is managed by your cloud provider. You're not coding your own applications, but you're simply consuming an application that the service provider has given to you that is already prepared for use. You're not responsible for deploying or maintaining or running the application. You're only responsible to use the application. An easy way to understand this would be with the help of certain examples. Think about Gmail or Office 365. Now, these are categorized as software as a service solutions. So, if you're using Gmail, you do not do any engineering, you do not do any administrative work, you do not code, but you simply start using Gmail as a service via a browser sitting on your computer that has internet. Now there's another exciting model that we're going to talk about. It is called as function as a service, also called as serverless. Serverless is very different from the traditional application architecture. With serverless, everything is abstracted. You're not even deploying whole applications. You are simply deploying small, single purpose functions or code. Now, with serverless, it doesn't mean that there is no server. It's actually a misnomer, yeah? There's some kind of a server running in the cloud provider's data center. So it just means the term serverless just means that you do not have to think about the server. That layer is completely abstracted. You simply deploy the small single purpose functions and you pay for the compute resources that are used by your code or used by your functions. So you never have to think about servers or instances or scalability. It all just happens for you automatically. There are certain examples that I could talk about when it comes to serverless or function as a service is when it comes to Amazon, you got AWS Lambda. And Amazon has a larger AWS serverless platform that includes a few other features in addition to Lambda. In Azure, it's called as Azure Functions. Google Cloud, it's called as Google Cloud Functions. And all these three from different cloud providers are categorized as serverless or function as a service offering. Remember that in function as a service or in serverless computing, you do not have to worry about the underlying infrastructure. You just have to worry about your code and you push it to one of those serverless services provided by your cloud provider. All of these different types of cloud architectures take advantage of the DevOps tools and concepts. So whether you're doing infrastructure as a service, platform as a service, software as a service, or serverless, the tools in the DevOps world will help you enable and implement the DevOps culture.